Section 8.4, Developing the Client. In the OAuth 2 authorization dance, the client application's role is to obtain an access token and make requests to the resource server on behalf of the user. Because we're using OAuth 2's authorization code flow, that means that when the client application determines that the user has not yet been authenticated, it should redirect the user's browser to the authorization server to get consent from the user. Then, when the authorization server redirects control back to the client must exchange the authorization code it receives for the access token. First things first, the client will need Spring Security's OAuth 2 client support in its class path. The following starter dependency makes that happen. Not only does this give the application OAuth 2 client capabilities that we'll exploit in a moment, but it also transitively brings in Spring Security itself. This enables us to write some security configuration for the application. The following security filter chain bean sets up Spring Security so that all requests require authentication. What's more, this security filter chain bean also enables the client-side bits of OAuth 2. Specifically, it sets up a login page at the path/OAuth2/authorization/taco-admin-client. But this is no ordinary login page that takes a username and password. Instead, it accepts an authorization code, exchanges it for an access token, and uses the access token to determine the identity of the user. Put another way, this is the path that the authorization server will redirect to after the user has granted permission. We also need to configure details about the authorization server and our application's OAuth 2 client details. That is done in configuration properties, such as in the following application.yml file, which configures a client named taco-admin-client. This registers a client with the Spring Security OAuth 2 client named taco-admin-client. The registration details include the client's credentials, client-ID and client-secret, the grant type, authorization-grant-type, the scopes being requested, scope, and the redirect URI, redirect-URI. Notice that the value given to redirect-URI has a placeholder that references the client's registration ID, which is taco-admin-client. Consequently, the redirect URI is set to this link, which has the same path that we configured as the OAuth 2 login earlier. But what about the authorization server itself? Where do we tell the client that it should redirect the user's browser? That's what the provider property does, albeit indirectly. The provider property is set to Taco Cloud, which is a reference to a separate set of configuration that describes the Taco Cloud provider's authorization server. That provider configuration is configured in the same application.yml file like this. The only property required for a provider configuration is issuer-URI. This property identifies the base URI for the authorization server. In this case, it refers to a server host whose name is auth server. Assuming that you are running these examples locally, this is just another alias for localhost. On most Unix-based operating systems, this can be added in your /etc/hosts file with the following line. Refer to documentation for your operating system for details on how to create custom host entries if /etc/hosts isn't what works on your machine. Building on the base URL, Spring Security's OAuth 2 client will assume reasonable defaults for the authorization URL, token URL, and other authorization server specifics. But if for some reason the authorization server you're working with differs from those default values, you can explicitly configure authorization details like this. We've seen most of these URIs, such as the authorization, token, and JWK set URIs already. The user-info-URI property is new, however. This URI is used by the client to obtain essential user information, most notably the user's username. A request to that URI should return a JSON response that includes the property specified in user-name-attribute to identify the user. Note, however, when using Spring Authorization Server, you do not need to create the endpoint for that URI. Spring Authorization Server will expose the user info endpoint automatically. Now all of the pieces are in place for the application to authenticate and obtain an access token from the authorization server. Without doing anything more, you could fire up the application, make a request to any URL on that application, and be redirected to the authorization server for authorization. When the authorization server redirects back, then the inner workings of Spring Security's OAuth 2 client library will exchange the code it receives in the redirect for an access token. Now, how can we use that token? Let's suppose that we have a service bean that interacts with the Taco Cloud API using REST template. The following REST ingredient service implementation shows such a class that offers two methods, one for fetching a list of ingredients and another for saving a new ingredient. The HTTP GET request for the /ingredients endpoint isn't secured, so the findAll method should work fine, as long as the Taco Cloud API is listening on localhost, port 8080. But the addIngredient method is likely to fail with an HTTP 401 response, because we've secured post requests to /ingredients to require writeIngredients scope. The only way around this is to submit an access token with writeIngredients scope in the request's authorization header. Fortunately, Spring Security's OAuth 2 client should have the access token handy after completing the authorization code flow. All we need to do is make sure that the access token ends up in the request. To do that, let's change the constructor to attach a request interceptor to the REST template it creates as follows. The constructor now takes a string parameter that is the access token. Using this token, it attaches a client request interceptor that adds the authorization header to every request made by the REST template, such that the header's value is bearer, followed by the token value. In the interest of keeping the constructor tidy, the client interceptor is created in a separate private helper method. Only one question remains: where does the access token come from? The following bean method is where the magic happens. To start, notice that the bean is declared to be request scoped using the @requestScope annotation. This means that a new instance of the bean will be created on every request. The bean must be request scoped because it needs to pull the authentication from the security context, which is populated on every request by one of Spring Security's filters. There is no security context at application startup time when default scoped beans are created. Before returning a REST ingredient service instance, the bean method checks to see that the authentication is, in fact, implemented as OAuth 2 authentication token. If so, that means it will have the token. It then verifies that the authentication token is for the client named taco-admin-client. If so, then it extracts the token from the authorized client and passes it through the constructor for REST ingredient service. With that token in hand, REST ingredient service will have no trouble making requests to the Taco Cloud API's endpoints on behalf of the user who authorized the application. Summary: OAuth 2 security is a common way to secure APIs that is more robust than simple HTTP basic authentication. An authorization server issues access tokens for a client to act on behalf of a user when making requests to an API, or on its own behalf in the case of client token flow. A resource server sits in front of an API to verify that valid, non-expired tokens are presented with the scope necessary to access API resources. Spring Authorization Server is an experimental project that implements an OAuth 2 authorization server. Spring Security provides support for creating a resource server, as well as creating clients that obtain access tokens from the authorization server and pass those tokens when making requests through the resource server. Chapter 9. Sending Messages Asynchronously. This chapter covers asynchronous messaging, sending messages with JMS, RabbitMQ, and Kafka, pulling messages from a broker, listening for messages. It's 4:55 p.m. on Friday. You're minutes away from starting a much-anticipated vacation. You have just enough time to drive to the airport and catch your flight. But before you pack up and head out, you need to be sure your boss and colleagues know the status of the work you've been doing so that on Monday they can pick up where you left off. Unfortunately, some of your colleagues have already skipped out for the weekend, and your boss is tied up in a meeting. What do? The most practical way to communicate your status and still catch your plane is to send a quick email to your boss and your colleagues, detailing your progress and promising to send a postcard. You don't know where they are or when they'll read the email, but you do know they'll eventually return to their desks and read it. Meanwhile, you're on your way to the airport. Synchronous communication, which is what we've seen with REST, has its place. But it's not the only style of inter-application communication available to developers. Asynchronous messaging is a way of indirectly sending messages from one application to another without waiting for a response. This indirection affords looser coupling and greater scalability between the communicating applications. In this chapter, we're going to use asynchronous messaging to send orders from the Taco Cloud website to a separate application in the Taco Cloud kitchens, where the tacos will be prepared. We'll consider 3 options that Spring offers for asynchronous messaging: the Java Message Service, JMS, RabbitMQ and Advanced Message Queuing Protocol, AMQP, and Apache Kafka. In addition to the basic sending and receiving of messages, we'll look at Spring's support for message-driven POJOs, a way to receive messages that resembles Enterprise Java Beans message-driven beans, MDBs. Section 9.1, Sending Messages with JMS. JMS is a Java standard that defines a common API for working with message brokers. First introduced in 2001, JMS has been the go-to approach for asynchronous messaging in Java for a very long time. Before JMS, each message broker had a proprietary API, making an application's messaging code less portable between brokers. But with JMS, all compliant implementations can be worked with via a common interface, in much the same way that JDBC has given relational database operations a common interface. Spring supports JMS through a template-based abstraction known as JMS Template. Using JMS Template, it's easy to send messages across queues and topics from the producer side and to receive those messages on the consumer side. Spring also supports the notion of message-driven POJOs, simple Java objects that react to messages arriving on a queue or topic in an asynchronous fashion. We're going to explore Spring's JMS support, including JMS Template and message-driven POJOs. Our focus will be on Spring's support for messaging with JMS. But if you want to know more about JMS, then have a look at ActiveMQ in Action by Bruce Snyder, Dayan Bosanats, and Rob Davies. Before you can send and receive messages, you need a message broker that's ready to relay those messages between producers and consumers. Let's kick off our exploration of Spring JMS by setting up a message broker in Spring. Section 9.1.1, Setting up JMS. Before you can use JMS, you must add a JMS client to your project's build. With Spring Boot, that couldn't be any easier. All you need to do is add a starter dependency to the build. First, though, you must decide whether you're going to use Apache ActiveMQ or the newer Apache ActiveMQ Artemis broker. If you're using ActiveMQ, you'll need to add the following dependency to your project's pom.xml file. If ActiveMQ Artemis is the choice, the starter dependency should look like this. When using the Spring Initializer, or your IDE's front end for the initializer, you can also select either of these options as starter dependencies for your project. They are listed as Spring for Apache ActiveMQ 5 and Spring for Apache ActiveMQ Artemis, as shown in the screenshot in Figure 9.1 from this link. Artemis is a next-generation re-implementation of ActiveMQ, effectively making ActiveMQ a legacy option. Therefore, for Taco Cloud, you're going to choose Artemis. But the choice ultimately has little impact on how you'll write the code that sends and receives messages. The only significant differences will be in how you configure Spring to create connections to the broker. Running an Artemis broker. You'll need an Artemis broker running to be able to run the code presented in this chapter. If you don't already have an Artemis instance running, you can, following the instructions from the Artemis documentation at this link. By default, Spring assumes that your Artemis broker is listing on localhost at port 61616. That's fine for development purposes, but once you're ready to send your application into production, you'll need to set a few properties that tell Spring how to access the broker. The properties you'll find most useful are listed in Table 9.1. For example, consider the following entry from an application.yml file that might be used in a non-development setting. This sets up Spring to create broker connections to an Artemis broker listening at artemis.tacocloud.com, port 61617. It also sets the credentials for the application that will be interacting with that broker. The credentials are optional, but they're recommended for production deployments. If you were to use ActiveMQ instead of Artemis, you'd need to use the ActiveMQ specific properties listed in Table 9.2. Notice that instead of offering separate properties for the broker's hostname and port, an ActiveMQ broker's address is specified with a single property, spring.activemq.broker-URL. The URL should be a TCP://URL, as shown in the following YAML snippet. Whether you choose Artemis or ActiveMQ, you shouldn't need to configure these properties for development when the broker is running locally. If you're using ActiveMQ, you will, however, need to set the spring.activemq.inmemory property to false to prevent Spring from starting an in-memory broker. An in-memory broker may seem useful, but it's helpful only when you'll be consuming messages from the same application that publishes them, which has limited usefulness. Instead of using an embedded broker, you'll want to install and start an Artemis or ActiveMQ broker before moving on. Rather than repeat the installation instructions here, I refer you to the broker documentation for details. Artemis at this link. ActiveMQ at this link. With the JMS starter in your build and a broker waiting to ferry messages from one application to another, you're ready to start sending messages. Section 9.1.2 Sending Messages with JMS Template. With the JMS starter dependency, either Artemis or ActiveMQ, in your build, Spring Boot will auto-configure a JMS template, among other things, that you can inject and use to send and receive messages. JMS template is the centerpiece of Spring's JMS integration support. Much like Spring's other template-oriented components, JMS template eliminates a lot of boilerplate code that would otherwise be required to work with JMS. Without JMS template, you'd need to write code to create a connection and session with the message broker and more code to deal with any exceptions that might be thrown in the course of sending a message. JMS template focuses on what you really want to do: send a message. JMS template has several methods that are useful for sending messages, including the following. As you can see, there are really only two methods, send and convert and send, each overridden to support different parameters. And if you look closer, you'll notice that the various forms of convert and send can be broken into two subcategories. In trying to understand what all of these methods do, consider the following breakdown. 3 send methods require a message creator to manufacture a message object. 3 convert and send methods accept an object and automatically convert that object into a message behind the scenes. 3 convert and send methods automatically convert an object to a message, but also accept a message post processor to allow for customization of the message before it's sent. Moreover, each of these 3 method categories is composed of 3 overriding methods that are distinguished by how the JMS destination, queue, or topic is specified, as follows. One method accepts no destination parameter and sends the message to a default destination. One method accepts a destination object that specifies the destination for the message. One method accepts a string that specifies the destination for the message by name. Putting these methods to work, consider JMS order messaging service in the next listing, which uses the most basic form of the send method. The send order method calls jms.send, passing in an anonymous inner class implementation of message creator. That implementation overrides create message to create a new object message from the given taco order object. Because the JMS-specific JMS order messaging service implements the more generic order messaging service interface, we can put this service to work by injecting it into the Order API controller and calling send order when an order is created, as shown here. Now, when you create an order through the Taco Cloud website, a message should be sent to the broker for routing to another application that will receive the order. We don't yet have anything to receive that message, though. Even so, you can use the Artemis console to view the contents of the queue. See the Artemis documentation at this link for details on how to do this. I'm not sure about you, but I think the code in Listing 9.1, although straightforward, is a bit clumsy. The ceremony involved in declaring an anonymous inner class complicates an otherwise simple method call. Recognizing that message creator is a functional interface, you can tidy up the send order method a bit with a lambda, as shown next. But notice that the call to jms.send doesn't specify a destination. For this to work, you must also specify a default destination name with the spring.jms.template.default-destination property. For example, you could set the property in your application.yml file like this. In many cases, using a default destination is the easiest choice. It lets you specify the destination name once, allowing the code to be concerned only with sending messages without regard for where they're being sent. But if you ever need to send a message to a destination other than the default destination, you'll need to specify that destination as a parameter to send. One way of doing that is by passing a destination object as the first parameter to send. The easiest way to do this is to declare a destination bean and then inject it into the bean that performs messaging. For example, the following bean declares the Taco Cloud order queue destination. This bean method can be added to any configuration class in the application that will be sending or receiving messages via JMS. For the sake of organization, it's best to add it to a configuration class designated for messaging configuration, such as messaging config. It's important to note that the active MQ used here is actually from Artemis, from the org.apache.activemq.artemis.jms.client package. If you're using ActiveMQ, not Artemis, there's also a class named ActiveMQQ from the org.apache.activemq.command package. If this destination bean is injected into JMS order messaging service, you can use it to specify the destination when calling send as follows. Specifying the destination with a destination object like this affords you the opportunity to configure the destination with more than just the destination name. But in practice, you'll almost never specify anything more than the destination name. It's often easier to just send the name as the first parameter to send, as shown here. Although the send method isn't particularly difficult to use, especially when the message creator is given as a lambda, a sliver of complexity is added by requiring that you provide a message creator. Wouldn't it be simpler if you needed to specify only the object that's to be sent, and optionally the destination? That describes succinctly how convert and send works. Let's take a look. Converting messages before sending. The JMS template convert and send method simplifies message publication by eliminating the need to provide a message creator. Instead, you pass the object that's to be sent directly to convert and send, and the object will be converted into a message before being sent. For example, the following re-implementation of send order uses convert and send to send a taco order to a named destination. Just like the send method, convert and send will accept either a destination or string value to specify the destination, or you can leave out the destination altogether to send the message to the default destination. Whichever form of convert and send you choose, the taco order passed into convert and send is converted into a message before it's sent. Under the covers, this is achieved with an implementation of Message Converter that does the dirty work of converting application domain objects to message objects. Configuring a message converter. Message converter is a Spring-defined interface that has only the following two methods to be implemented. Although this interface is simple enough to implement, you often won't need to create a custom implementation. Spring already offers a handful of implementations, such as those described in Table 9.3. Simple message converter is the default, but it requires that the object being sent implement serializable. This may be a good idea, but you may prefer to use one of the other message converters, such as mapping Jackson 2 message converter, to avoid that restriction. To apply a different message converter, all you must do is declare an instance of the chosen converter as a bean. For example, the following bean declaration will enable mapping Jackson 2 message converter to be used instead of simple message converter. This bean method can be placed in any configuration class in the application that sends and receives messages with JMS, including alongside the destination bean in messaging config. Notice that you called setTypeID property name on the mapping Jackson 2 message converter before returning it. This is very important because it enables the receiver to know what type to convert an incoming message to. By default, it will contain the fully qualified class name of the type being converted. But this method is somewhat inflexible, requiring that the receiver also have the same type with the same fully qualified class name. To allow for more flexibility, you can map a synthetic type name to the actual type by calling setTypeID mappings on the message converter. For example, the following change to the message converter bean method maps a synthetic taco order type ID to the taco order class. Instead of the fully qualified class name being sent in the messages_type ID property, the value taco order will be sent. In the receiving application, a similar message converter will have been configured, mapping taco order to its own understanding of what an order is. That implementation of an order may be in a different package, have a different name, and even have a subset of the sender's taco order properties. Post-processing messages. Let's suppose that in addition to its lucrative web business, Taco Cloud has decided to open a few brick-and-mortar taco joints. Given that any of their restaurants could also be a fulfillment center for the web business, they need a way to communicate the source of an order to the kitchens at the restaurants. This will enable the kitchen staff to employ a different process for store orders than for web orders. It would be reasonable to add a new source property to the taco order object to carry this information, populating it with web for orders placed online and with store for orders placed in the stores. But that would require a change to both the website's taco order class and the kitchen application's taco order class when, in reality, it's information that's required only for the taco preparers. An easier solution would be to add a custom header to the message to carry the order's source. If you were using the send method to send the taco orders, this could easily be accomplished by calling setStringProperty on the message object as follows. The problem here is that you aren't using send. By choosing to use convert and send, the message object is created under the covers, and you don't have access to it. Fortunately, you have a way to tweak a message created under the covers before it's sent. By passing in a message post processor as the final parameter to convert and send, you can do whatever you want with the message after it has been created. The following code still uses convert and send, but it also uses a message post processor to add the x_order_source header before the message is sent. You may have noticed that message post processor is a functional interface. This means that you can simplify it a bit by replacing the anonymous inner class with a lambda, as shown here. Although you need this particular message post processor for only this one call to convert and send, you may find yourself using the same message post processor for several different calls to convert and send. In those cases, perhaps a method reference, shown next, is a better choice than a lambda, avoiding unnecessary code duplication. You've now seen several ways of sending messages, but it does no good to send a message if nobody ever receives it. Let's look at how you can receive messages with Spring JMS. Section 9.1.3 Receiving JMS Messages. When it comes to consuming messages, you have the choice of a pull model, where your code requests a message and waits until one arrives, or a push model, in which messages are handed to your code as they become available. JMS template offers several methods for receiving messages, but all of them use a pull model. You call one of those methods to request a message, and the thread is blocked until a message is available, which could be immediately or it might take a while. On the other hand, you also have the option of using a push model, wherein you define a message listener that's invoked any time a message is available. Both options are suitable for a variety of use cases. It's generally accepted that the push model is the best choice because it doesn't block a thread, but in some use cases, a listener could be overburdened if messages arrive too quickly. The pull model enables a consumer to declare that they're ready to process a new message. Let's look at both ways of receiving messages. We'll start with the pull model offered by JMS template. Receiving with JMS template. JMS template offers several methods for pulling methods from the broker, including the following. As you can see, these 6 methods mirror the send and convert and send methods from JMS template. The receive methods receive a raw message, whereas receive and convert methods use a configured message converter to convert messages into domain types. And for each of these, you can specify either a destination or a string containing the destination name, or you can pull a message from the default destination. To see these in action, you'll write some code that pulls a taco order from the tacocloud.order.queue destination. The following listing shows order receiver, a service component that receives order data using JMS template.receive. Here you've used a string to specify the destination from which to pull an order. The receive method returns an unconverted message, but what you really need is the taco order that's inside of the message. So the very next thing that happens is that you use an injected message converter to convert the message. The type ID property in the message will guide the converter in converting it to a taco order, but it's returned as an object that requires casting before you can return it. Receiving a raw message object might be useful in some cases where you need to inspect the message's properties and headers, but often you need only the payload. Converting that payload to a domain type is a 2-step process and requires that the message converter be injected into the component. When you care only about the message's payload, receive and convert is a lot simpler. The next listing shows how JMS order receiver could be reworked to use receive and convert instead of receive. This new version of JMS order receiver has a receive order method that has been reduced to only 1 line. Plus, you no longer need to inject a message converter, because all of the message conversion will be done behind the scenes in receive and convert. Before moving on, let's consider how receive order might be used in the Taco Cloud kitchen application. A food preparer at one of Taco Cloud's kitchens might push a button or take some action to indicate that they're ready to start building tacos. At that point, receive order would be invoked, and the call to receive or receive and convert would block. Nothing else would happen until an order message is ready. Once an order arrives, it will be returned from receive order, and its information will be used to display the details of the order for the food preparer to get to work. This seems like a natural choice for a pull model. Now let's see how a push model works by declaring a JMS listener. Declaring message listeners. Unlike the pull model, where an explicit call to receive or receive and convert was required to receive a message listener is a passive component that's idle until a message arrives. To create a message listener that reacts to JMS messages, you simply annotate a method in a component with @JMSListener. The next listing shows a new order listener component that listens passively for messages, rather than actively requesting them. The receive order method is annotated with JMS listener to listen for messages on the tacocloud.order.queue destination. It doesn't deal with JMS template, nor is it explicitly invoked by your application code. Instead, framework code within Spring waits for messages to arrive on the specified destination, and when they arrive, the receive order method is invoked automatically with the message's taco order payload as a parameter. In many ways, the JMS listener annotation is like one of Spring MVC's request mapping annotations, such as @getMapping or @postMapping. In Spring MVC, methods annotated with one of the request mapping methods react to requests to a specified path. Similarly, methods that are annotated with @JMSListener react to messages that arrive in a destination. Message listeners are often touted as the best choice because they don't block and are able to handle multiple messages quickly. In the context of the Taco Cloud application, however, perhaps they aren't the best choice. The food preparers are a significant bottleneck in the system and may not be able to prepare tacos as quickly as orders come in. A food preparer may have half fulfilled an order when a new order is displayed on the screen. The kitchen user interface would need to buffer the orders as they arrive to avoid overburdening the kitchen staff. That's not to say that message listeners are bad. On the contrary, they're a perfect fit when messages can be handled quickly. But when the message handlers need to be able to ask for more messages on their own timing, the pull model offered by JMS template seems more fitting. Because JMS is defined by a standard Java specification and supported by many message broker implementations, it's a common choice for messaging in Java. But JMS has a few shortcomings, not the least of which is that as a Java specification, its use is limited to Java applications. Newer messaging options, such as RabbitMQ and Kafka, address these shortcomings and are available for other languages and platforms beyond the JVM. Let's set JMS aside and see how you could have implemented your taco order messaging with RabbitMQ. Section 9.2. Working with RabbitMQ and AMQP. As arguably the most prominent implementation of AMQP, RabbitMQ offers a more advanced message routing strategy than JMS. Whereas JMS messages are addressed with the name of a destination from which the receiver will retrieve them, AMQP messages are addressed with the name of an exchange and a routing key, which are decoupled from the queue to which the receiver is listening. This relationship between an exchange and queues is illustrated in Figure 9.2. When a message arrives at the RabbitMQ broker, it goes to the exchange for which it was addressed. The exchange is responsible for routing it to one or more queues, depending on the type of exchange, the binding between the exchange and queues, and the value of the message's routing key. There are several different kinds of exchanges, including the following. Default, a special exchange that's automatically created by the broker. It routes messages to queues whose name is the same as the message's routing key. All queues will automatically be bound to the default exchange. Direct, routes messages to a queue whose binding key is the same as the message's routing key. Topic, routes a message to one or more queues where the binding key, which may contain wildcards, matches the message's routing key. Fanout, routes messages to all bound queues without regard for binding keys or routing keys. Headers, similar to a topic exchange, except that routing is based on message header values rather than routing keys. Dead letter, a catch-all for any messages that are undeliverable, meaning they don't match any defined exchange to queue binding. The simplest forms of exchanges are default and fanout. These roughly correspond to a JMS queue and topic, but the other exchanges allow you to define more flexible routing schemes. The most important thing to understand is that messages are sent to exchanges with routing keys, and they're consumed from queues. How they get from an exchange to a queue depends on the binding definitions and what best suits your use cases. Which exchange type you use and how you define the bindings from exchanges to queues has little bearing on how messages are sent and received in your Spring applications. Therefore, we'll focus on how to write code that sends and receives messages with Rabbit. Note: for a more detailed discussion on how best to bind queues to exchanges, see RabbitMQ in Depth by Gavin Roy, or RabbitMQ in Action by Alvaro Videla and Jason J. W. Williams. Section 9.2.1. Adding RabbitMQ to Spring. Before you can start sending and receiving RabbitMQ messages with Spring, you'll need to add Spring Boot's AMQP starter dependency to your build in place of the Artemis or ActiveMQ starter you added in the previous section, as shown here. Adding the AMQP starter to your build will trigger auto-configuration that will create an AMQP connection factory and Rabbit template beans, as well as other supporting components. Simply adding this dependency is all you need to do to start sending and receiving messages from a RabbitMQ broker with Spring. But there are a handful of useful properties you'll want to know about, listed in Table 9.4. For development purposes, you'll probably have a RabbitMQ broker that doesn't require authentication running on your local machine, listening on port 5672. These properties likely won't get much use while you're still in development, but they'll no doubt prove useful when your applications move into production. Running a RabbitMQ broker. If you don't already have a RabbitMQ broker to work with, you have several options for running RabbitMQ on your local machine. See the official RabbitMQ documentation at this link for the latest instructions for running RabbitMQ. For example, suppose that you move into production. Your RabbitMQ broker is on a server named rabbit.tacocloud.com, listening on port 5673, and requiring credentials. In that case, the following configuration in your application.yml file will set those properties when the prod profile is active. Now that RabbitMQ is configured in your application, it's time to start sending messages with Rabbit template. Section 9.2.2 Sending Messages with Rabbit Template. At the core of Spring's support for RabbitMQ messaging is Rabbit Template. Rabbit Template is similar to JMS Template and offers a similar set of methods. As you'll see, however, some subtle differences align with the unique way that RabbitMQ works. With regard to sending messages with Rabbit Template, the send and convert and send methods parallel the same named methods from JMS Template. But unlike the JMS Template methods, which route messages only to a given queue or topic, Rabbit Template methods send messages in terms of exchanges and routing keys. Here are a few of the most relevant methods for sending messages with Rabbit Template. Footnote 1. These methods are defined by AMQP template, an interface implemented by Rabbit Template. As you can see, these methods follow a pattern similar to their twins in JMS Template. The first three send methods all send a raw message object. The next three convert and send methods accept an object that will be converted to a message behind the scenes before being sent. The final three convert and send methods are like the previous three, but they accept a message post processor that can be used to manipulate the message object before it's sent to the broker. These methods differ from their JMS template counterparts in that they accept string values to specify an exchange and routing key, rather than a destination name or destination object. The methods that don't take an exchange will have their messages sent to the default exchange. Likewise, the methods that don't take a routing key will have their messages routed with a default routing key. Let's put Rabbit Template to work sending taco orders. One way you can do this is by using the send method, as shown in listing 9.5. But before you can call send, you'll need to convert a taco order object to a message. That could be a tedious job if not for the fact that Rabbit Template makes its message converter readily available with a getMessageConverter method. You'll notice that Rabbit Order Messaging Service implements Order Messaging Service, just like JMS Order Messaging Service. This means that it can be injected into Order API Controller the same way to send order messages when an order is placed. Because we don't yet have anything to receive those messages, though, you can use the RabbitMQ browser-based management console. See this link for details on how to enable and use the RabbitMQ console. Once you have a message converter in hand, it's simple work to convert a taco order to a message. You must supply any message properties with a message properties, but if you don't need to set any such properties, a default instance of message properties is fine. Then all that's left is to call send, passing in the exchange and routing key, both of which are optional, along with the message. In this example, you're specifying only the routing key, tacocloud.order, along with the message, so the default exchange will be used. Speaking of default exchanges, the default exchange name is an empty string. which corresponds to the default exchange that's automatically created by the RabbitMQ broker. Likewise, the default routing key is an empty string, whose routing is dependent upon the exchange and bindings in question. You can override these defaults by setting the spring.rabbitmq.template.exchange and spring.rabbitmq.template.routing-key properties as follows. In this case, all messages sent without specifying an exchange will automatically be sent to the exchange whose name is tacocloud.order. If the routing key is also unspecified in the call to send or convert and send, the messages will have a routing key of kitchens.central. Creating a message object from the message converter is easy enough, but it's even easier to use convert and send to let Rabbit Template handle all of the conversion work for you, as shown next. Configuring a message converter. By default, message conversion is performed with Simple Message Converter, which is able to convert simple types, like string, and serializable objects to message objects. But Spring offers several message converters for Rabbit Template, including the following. Jackson to JSON Message Converter converts objects to and from JSON using the Jackson to JSON processor. Marshalling Message Converter converts using a Spring marshaller and unmarshaller. Serializer Message Converter converts string and native objects of any kind using Spring's serializer and deserializer abstractions. Simple Message Converter converts string, byte arrays, and serializable types. Content Type Delegating Message Converter delegates to another message converter based on the content type header. Messaging Message Converter delegates to an underlying message converter for the message conversion and to an AMQP header converter for the headers. If you need to change the message converter, just configure a bean of type Message Converter. For example, for JSON-based message conversion, you can configure a Jackson to JSON message converter like this. Spring Boot auto-configuration will discover this bean and inject it into Rabbit Template in place of the default message converter. Setting message properties. As with JMS, you may need to set some headers in the messages you send. For example, let's say you need to send an x_order_source for all orders submitted through the TacoCloud website. When creating your own message objects, you can set the header through the message properties instance you give to the message converter. Revisiting the send order method from listing 9.5, you only need one additional line of code to set the header, as shown next. When using convert and send, however, you don't have quick access to the message properties object. A message post processor can help you with that, though, as shown here. Here, you supply convert and send with an anonymous inner class implementation of message post processor. In the post process message method, you pull the message properties from the message and then call set header to set the x_order_source header. Now that you've seen how to send messages with Rabbit Template, let's switch our focus over to the code that receives messages from a RabbitMQ queue. Section 9.2.3 Receiving Messages from RabbitMQ. You've seen that sending messages with Rabbit Template doesn't differ much from sending messages with JMS Template. And as it turns out, receiving messages from a RabbitMQ queue isn't very different than from JMS. As with JMS, you have the following two choices. Pulling messages from a queue with Rabbit Template, having messages pushed to a @RabbitListener annotated method. Let's start by looking at the pull-based RabbitTemplate.receive method. Receiving messages with Rabbit Template. Rabbit Template comes with several methods for pulling messages from a queue. A few of the most useful ones are listed here. These methods are the mirror images of the send and convert and send methods described earlier. Whereas send is used to send raw message objects, receive receives raw message objects from a queue. Likewise, receive and convert receives messages and uses a message converter to convert them into domain objects before returning them.